Yeah, welcome back. Yeah, Dr. D. Srinivasarao is going to deliver. um, just a minute. Srinivas, you are there, right? Yes, sir.
Yes, sir. I'm here.
Yeah. Sir is going to show you on the simulation, MATLAB simulation or power converters, what sir has discussed in the today morning. Going to show you the simulation. Over to DSR.
Yes, sir. Next. Yeah, good afternoon, everyone. In the morning session, we discussed about some of the basic things about the multi-level calculation and reduce switch count multi-level inverters, right? So now we will discuss about their modulation techniques. You know that, right? So modulation techniques are required to operate the inverter as in the current control mode or the voltage control mode. So first we'll discuss about the modulation techniques which are commonly used for multi-level converters, right? So next after that we'll discuss about the grid integration of these converters. So you know that, right? So conventional PWM methods like sine PWM technique or the space vector PWM techniques, so which are not conventional PWM technique like sine PWM technique, space vector PWM technique, and the selective harmonic elimination methods are not directly applicable for these multi-level converters. So we need to do some modifications, right? So as you know that, right? So this is known as the multi-level modulation techniques, right? So there are basically two types. So one is the space vector based algorithms and the voltage based or voltage level based algorithms. So in case of space vector modulation techniques or the space vector based algorithms, we will treat this inverter as entire unit, right? So whereas in PWM technique or the voltage based algorithms, so we have a carrier signal will be there, modulating signal will be there, and each phase is controlled separately. So here each phase is controlled separately. So whereas in space vector based algorithms, so all the three phases are controlled together. So in case of space vector based algorithms, so we have space vector modulation techniques is there and the space vector control method is there. And 2D algorithms are there, 3D algorithms are there, and we have again so three-leg inverter based or sometimes we need to use four-leg inverters, especially for the power quality improvement techniques. So where the fourth leg is used to control the neutral current. So these kind of algorithms, so we normally prefer. And also there are other algorithms is there. So that is the nearest level control, nearest level control. So that is one of the method. So that is commonly used for multi-level inverters. So come to this carrier-based approaches like voltage-based algorithms. So we have this multi-carrier PWM techniques, and right, and another one is the hybrid modulation, selective harmonic elimination. As we discussed, this is nearest level control. So this nearest level control, so this is used for where the number of levels are extremely high. For example, 20, 25 level inverter or higher than the 50 level inverter. In sometimes in HVDC applications, so we normally have 201 levels or even 400 levels, like that it will be there. So in that such cases, we normally prefer this nearest level control algorithm. Right. And the selective harmonic elimination is similar to the selective harmonic
ఎంత టైం
elimination that is
పడుతుంది
used for
ఇక్కడికి?
two level.
15 minutes. ఆ?
So whereas this hybrid modulation,
టింగ్ బయలుదేరుతావా?
so whereas this hybrid modulation technique, so whereas this hybrid modulation technique, so this is normally used for the asymmetrical cascade edge bridge converters. Like if you have a mixed ratio of DC sources, under this case, this is preferred. Right. So this multi-carrier PWM techniques. So this is normally divided into two types. So one is the phase shifted PWM and the level shifted PWM. So in case of phase shifted PWM, there is no other methods are there. And in case of level shifted PWM, so depending on the carrier arrangement, so we have this phase opposition disposition, alternate phase opposition disposition, and phase disposition PWM techniques are there. Right. So now we'll focus on this commonly used PWM methods such as this phase shifted PWM and the level shifted PWM. So as we discussed, so this is phase shifted PWM and the level shifted PWM. So these are the natural extension of sine PWM techniques, so which are used for the multi-level inverters. Right. So come to this phase shifted PWM technique. Right. So in this case, if you consider M level inverter, so in this case, if you consider M level inverter, you require M minus 1 carriers. Right. So each pair, if you observe that the number of switches in each phase for in case of cascade edge bridge or diode clamp or anything, right? So this is equal to 2 into M minus 1 devices are there. And you have one carrier signal and one modulating signal. So that will generate the firing pulse for the two devices, right? So which are in so which are in each opposite to each other, right? The pairing signals are complementary, right? So therefore you have a complementary pair is there. So for each complementary pair you have one modulating signal and one carrier signal. So that means for 2 into M minus 1 switches per phase you require so M minus 1 carrier signals. The modulating signal is same, but you need M minus 1 carrier signals. Okay? So these M minus 1 carrier signals so will be interact with the modulating signal, and accordingly the firing pulse is generated for each switch pair. Right? So meaning is that so each switch pair of switches you have a carrier signal, so which has a phase shift to each other. Right? So each carrier signal, so which is vary from +1 to -1. So each carrier signal, so which is vary from the +1 to -1, right? And you require a phase shift, and you need to maintain a phase shift between the carriers. So how much phase shift that is required? So that depends on the number of levels. So if you have a 5 level inverter, in this case, this is 360 degrees divided by 5 minus 1, 4. So you need to maintain 360 degrees by M minus 1. So that is the phase shift angle you are supposed to maintain. So this is the first carrier. If you want to have a second carrier, so which will be phase shifted like this, like this, like this. Right. So you have 4 carriers, and the fifth carriers and the first carriers will be obviously coincides. Okay. And you require M minus 1 triangle carriers, and all these triangle carriers have the same frequency. So all are having same frequency and same peak to peak value. So all are maybe some frame frequency FCR, and all must be vary from +1 to -1. But we need to maintain a phase shift among these carriers, right? So any two adjacent carriers, we need to maintain a phase shift. So that phase shift is given as 360 degrees by M minus 1. So this is the carrier arrangement for a phase shifted PWM. So this is also known as PS PWM. Right. So this is the arrangement for here. right? So this is the arrangement. So this is carrier 1, carrier 2, carrier 3, and carrier 4. Right. So here, if you observe that the cascade H bridge, or so if you remember the cascade H bridge converter, so here one switch is there, 1, 2, 3, 4. This is one H bridge, right? So in the second H bridge, let us assume it is 5, 7, 5, 6, 7, 8. Right? So this 1, 2, all these are all switches. Right? So this represent one phase. So there are four switches in each H bridge, right? Understood. So you have 8 switches are there and 4 carrier and modulating signal interactions will be there. So that means, so this 1 and 2, so this 1 and 2 is controlled by one carrier. Let us assume it is carrier 1. Right. Similarly, so this 5 and 6 are controlled by another carrier. So this carrier 2, and similarly 8 and 7 is controlled by carrier 3, and this 4 and 3 is controlled by carrier 4. So that means it is following some U shape. So first we say 1 and 2, this carrier 1, this is 1 and 2 devices, right? And this will be 5 and 6 device, and this is 8 and 7, and this is 4 and 3. So this way it will be controlled like U shape. If you observe that this is U shape. So this way, if you are controlling doing this, so each H bridge will be operating unipolar PWM mode. You know that, right? In single phase, you have two PWM techniques. So one is the unipolar PWM and the bipolar PWM. So in this way, so these H bridges or each H bridge will be operating the unipolar PWM mode. Understood? So you require 4 carriers, and each carrier will be interact with the modulating signal. Accordingly, it will generate the firing signal for a switch pair. So this 1 and 2 will be for carrier 1, 5 and 6 for the carrier 2, 8 and 7 for the carrier 3, and 4 and 2 for the carrier 4. Right. Similarly, if you have the flying capacitor multi-level inverter, as we discussed, flying capacitor multi-level inverters, we have top 1, 2, 3, 4 switch will be there, 4 switches on the upper side, and similarly, you have 4 dash, 3 dash, 2 dash, and 1 dash. As we discussed, the outer switches are complementary, right? So this means in this case, so this 1 required one carrier 1. So this is controlled by carrier 1. Right. So these two switches are controlled by carrier 2, and this is controlled by carrier 3, and this is controlled by carrier 4. Right. So this way, so we will give the firing signal for the individual devices. So you can see here, so this is for example of 7 level CHB. So this is 7 level CHB, and you require 6 carriers, and you need to maintain 60 degrees among each carrier. So this is the carrier arrangement, and we are comparing with a modulating signal, right? So comparing the carrier 1 and the modulating signal, so that will generate the switches here. This is for modulating signal, carrier 2, carrier 3, carrier 4, carrier 5, and carrier 6, right? So now if you observe the output voltage of each H bridge, so this is VH1, VH2, and VH3. So this is VH1, so this is VH2, and this is VH3. Right. So you know that, right? The sum of all H bridges, or you are measuring the voltage between this A and this neutral. So this is V or VAN, so which is equal to VH1 plus VH2 plus VH3. And also you can see that, right? So as we discussed, so this is also operating in unipolar PWM. You have positive off cycle and negative off cycle. So this is operating in unipolar PWM mode, right? So this is how we will implement a phase shifted PWM technique. Similarly, in case of level shifted PWM technique, in case of level shifted PWM technique. So here also each switch pair require one carrier signal, and also for M level inverter you require M minus 1 number of triangle carriers, and all are having the same frequency and same peak to peak amplitude. But here instead of maintaining a phase shift among the individual carriers, so here they are vertically disposed, right? So among these carriers are vertically disposed like this. So this is for 5 level inverter. So that means number of carriers are 4 here. And if you observe that, so we have the carrier pin, so which is between the plus 1 to minus 1. So this plus 1 to minus 1, so this is divided by 4 carriers. So that means the carrier 1 is varying from this carrier 1, so which is vary from 1 to zero point 0.5. So carrier 2, this red one, so which is varying from zero point 0.5 to 0, and the carrier 3, the cyan one, so that is varying from 0 to minus zero point 0.5, and the last one, so which is vary from minus zero point 0.5 to minus 1. So you have 4 carriers are there. So these 4 carriers, so will share vertically this region. So now the interaction of this modulating signal with this carrier one, you can see this is the interaction, right? So this is producing the firing signals, right? As we discussed, 1, 2, 3, 4, and like this, as we discussed, right? This is 1, 2, 3, 4, 5, 6, 7, 8, like this. So this will generate the switches for this one, and this is for this, and this is for 8, 7, right? 8, 7, this complementary will be the 7, 1, and this is 4, and this complementary will be the third switch in this one, right? So each carrier so will be interacted with the modulating signal, so accordingly it will generate the firing signals, right? So earlier one, so this is known as phase shifted PWM, and this is known as level shifted PWM. So if you observe the differences, first thing is that in case of phase shifted PWM, if you see that, right? So here these are the firing pulses. This is the firing pulse, all right. So if you observe this one, all are similar, right? All are almost identical, but there will be a small phase shift between this carrier. From here to here, so 90 degrees phase shift is there. From here to here, 90 degrees, and here to here, 90 degrees, and from here to here, another 90 degrees. Likewise. Okay. So here, all the devices are operating at the same frequency and same conduction periods. All our devices are operating at the same conduction period. Only thing is that so there will be a small phase shift between these pulses. So whereas in the level shift PWM technique, so here we observe that, so here thing is that, so in this case it is on for only 1, 2, 3, 4, 5, 5 instances. This is one, you have bigger pulse here, and you have 3 instances, you have one bigger pulse here, 2, 3, and this is also continuation of this pulse. This is actually, this is the continuation, 3 pulses, right? And whereas this one, this is 1, 2, 3, 4, 5, 6, 7, right? So each one or each device is having individual, or these conduction periods are not same, and the frequency of each switch, so that is also not same, right? So keep this in mind. So we'll discuss that what are the disadvantages and advantages if your conduction periods are same or the switching frequency of each device is same. So here, so completes performance. So again, we have 7-level inverter is there, right? So as we discussed, these are the carrier positions, right? So as discussed, so this is controlled by one carrier, 2, 3, 4, 5, 6, right? So this will be the output of the bridge 1. So this is output of bridge 2, and this is output of bridge 3. So if it's observed that, so this bridge 1 is on for only less period, this is the output voltage. So whereas this third bridge, so which is operate for a more amount of time. Right? Third bridge is operating for more amount of time. So that means the power delivered by this third one will be high, so when compared to the first one. Right? So that means, so we normally have some mismatches in the power distribution or the voltage across each edge bridge. So whereas in this case, right, so in this case, all are same. See here, all outputs are same. This one, right, and all are same. Just we have some phase shift. That's all. All these waveforms are same. So only we have some small phase shift is there. Understood? So if you see their actual performance or something like that, or PSPWM techniques, so when you are implementing for a 5-level inverter, so this one is the line voltage and this is phase voltage, and this is its corresponding harmonic spectrum. Right. So these are the results with phase shift PWM technique for a 5-level inverter. Right. So we have 9 levels here and we have 5 levels here, and the TH is around 29.76 percentage. And these are the four. So 1500 Hz carrier frequency, so 50 Hz modulating signal frequency. So therefore your frequency modulation index MF 1500 divided by 50, so is equal to 30. Right. And here these are the harmonic spectrum. So you can see that. So these are the sideband harmonics. And here the sideband harmonics are centered around this 120. Is centered around this 120. So how this 120 is achieved or how it is happening? So if you have M level inverter, in case of phase shift PWM technique, right? So as we discussed, each switch is operating for, or each switch is operating fixed frequency of FCR. That means each switch here, each switch is operating, that means each switch is operating same frequency of the carrier. That means it is operating a FCR frequency. So this is also operating FCR frequency, this is also operating FCR and FCR frequencies, right? So here all switches are operating at same frequency. So that means you have 4 carriers are there. So that means that there are 2 things you need to keep in mind. So one is the inverter frequency and the device frequency. So each device is operating at FCR frequency, right? But the overall inverter, so here, the overall inverter, so which is operating at M minus 1 times FCR frequency. This overall inverter is operating M minus 1 into FCR. So this will be the inverter frequency. So whereas FCR is the each switch frequency. In other words, it is the effective frequency of the inverter, right? So here FCR is, in case of FCR, it is 30, but it is M minus 1. M minus 1 is 5 minus 1, it is 4. So this is corresponding to 120, and you have this 120. So it is M minus 1 into MF. Right? So this is M minus 1 into FCR by M. Right? So inverter effective frequency is M minus 1 times MF, but each switch is operating at a frequency of FCR. Similarly, if you observe that, so level shift PWM technique, so in this case, same parameters, 1500 Hz, 1500 Hz, 50 Hz. Similarly, here also MF is 30. Right? But you observe that harmonics are centered around 30. Again, this is line voltage and this is phase voltage. And harmonics are centered around 30. So 30 is equal to MF frequency. And interesting thing is that the THD is just 17.58. So when compared to here THD is 29.76 and here it is 17.58 only. So the point is that why it is equal to the MF. Right. So here in this case, for example, in this case it is 1 kilohertz, right? So that means here MF is 20. So if you observe, if you count all the switchings of these 4 switches, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? If you count all these dots here, you will approximately get 20, including some small narrow pulses. Or theoretically, you will get 20 here. Right. So this 20 is equal to this one. So that means here each switch is not operating at carrier frequency like phase shift PWM. So whatever the carrier frequency is there, right? So that is distributed among the switches. So therefore here the inverter frequency is equal to carrier frequency. So frequency or effective frequency of the inverter is carrier frequency in case of level shift PWM. In case of phase shift PWM, so it is equal to n minus 1 times FCR. So this is for phase shift PWM. Understood? So that's why, so here the carriers are, the carriers are, or the harmonic spectrum is centered around the MF frequency. Similarly, you have 2 MF frequency and so on. So even though you have lower order harmonics, but their magnitude is very less. So in this case, just is 4%. So whereas here, so these peak values are more than 10%. So that's why THT is more. And observe that if you see this comparing these waveforms here, especially this region, you compare here this region, right? So here, so whatever if you observe, this is the best approximation of a sine wave. Right. So this is the best approximation of a sine wave. So that is obtained with the level shift PWM technique. So whereas this one, if you observe that, see we have some extra switchings here. So we have some extra switchings, especially in these regions, right? So we have some extra switchings. So that is not required. So that's why THD is, or THD performance is less when compared to the uh, level shift PWM technique. All right. So meaning is that, so this level shift PWM technique, so best harmonic performance in fact, so any PWM technique, so this is a benchmark one. So no one will not get the performance like this. So this is the best this is the best THD, so that one can obtain with any method. Right? So that's why every PWM method when they are inventing, right, so they will normally compare with this level shift PWM technique itself. All right. So that means level shift PWM produces the best PWM technique compared to the phase shift PWM, but the drawbacks are the unequal power distribution, unequal loss distribution. All the devices are not operating at the same frequency and all, right? So this is the comparison. So phase shift PWM device switching frequency is same for all, right? And this is different here. So conduction periods are same for PSPWM, and this is different. Line to TH is good here, so whereas you'll get the best performance. So inverter topology, another drawback is that the drawback with phase shift PWM is that, so this phase shift PWM cannot be utilized for flying, so diode clamped multi-level or neutral point clamped. So for NPC or the diode clamped multi-level inverters, so this phase shift PWM is not applicable. So because they don't have the switching redundancies, so meaning is that for if obtaining one voltage level, you normally require multiple paths. So that facility is not there in the uh, diode clamped inverter. So whereas this level shift PWM, so it will be applicable for any PWM or any inverter topology. So capacitor balancing, if you are using a capacitors, so that balancing is simple. So why it is simple means, because the device switching frequency, all devices are operating at same frequency, their conduction periods are same, therefore it is expected that the charging and discharging periods are also same. The charging and discharging periods also same, so therefore you can get the best THD performance. So whereas for level shift PWM, so it is poor. There are some methods are there like carrier rotation methods or some carrier rotation methods that will improve the performance. So this is one of the methods. So carrier rotation method. So here one carrier is there, right? This is one modulating signal, and if you observe that the green one, so green one is at first place. After completion of this modulating signal, it is moved to the second place, and it is moved to third place, and it is moved to the first place. And after 4 cycles, it is moved to the first place. So this is known as the carrier rotation techniques, right? Similarly, this is just a transposition of a transportation of conductors in case of transmission lines. See here, after if you see the performance of this four cycles, right, it is uniform. So there is another thing is that another carrier method, right? So we here just within that modulating period only, so we have transposed the carrier. So this is first carrier. So this, if you observe that green one, see here, right? So how this green one is changing its position from the one to stage one, two, three, four, and again it's moved to the fourth, first position. So here this carrier rotation techniques. So this is happening at every modulating cycle. So these two techniques are commonly used for improving the performance of. Here, the good thing is that, so this is equivalent to the level shift PWM technique, but best thing is that you can still maintain the carrier. We can maintain the all devices are operating the same frequency. See here, all devices are operating the same frequency. Understood. So now we will see how to do the simulation in the MATLAB.
Sinu sir,
Yes, sir.
yeah, participants are asking for a break.
Okay, sir.
We'll take a break before going to the simulation
Okay, okay, sir.
for 10 minutes. 10 minutes is fine, right?
Okay, sir.
We'll take a break over there and then we can start the MATLAB simulation. Srinu to DSL. Srinu, shall we start, Srinu sir?
So am I audible?
Yes, Srinu, audible.
Yes.
With the introduction, I think. You're audible, Srinu sir.
Yeah. So now we'll simulate this work in the MATLAB simulating environment. Right. So I consider I developed five level cascade edge bridge inverter. Right. So this is bridge one, right, and this is bridge two for A phase. So this is for bridge one and bridge two for B phase, and we have bridge one and bridge two for C phase. Right. So here we
Srinu
have four
sir,
switches in each phase. Yes, sir.
some Yana Reddy sir, I mean, do you have a doubt? You can unmute yourself and ask if there is any. No, he raised his hand, maybe accidentally. Okay, we'll see it later, Srinu sir. Okay.
So here this one, this entire thing, so it produces a five level cascade edge bridge, and we have a common ground point is there for the reference. And these are three terminals. So this is A phase terminal, right? This one A phase, and this is B phase, C phase. I connected some RL load, and some RL load or some value of R and L, right? And I measured the phase voltage, phase two, that is line voltage here, and phase two ground voltage, phase voltage is here. This is phase voltage. This is phase voltage, and this is line voltage. Right. And I consider each DC source as 200 volts. Just I connect some DC sources. That's all. Right. So now we will use the phase shift PWM technique. As we discussed, phase shift PWM technique requires four number of carriers. So this entire thing is the modulating signal generation for the A phase. So this is for B phase, and the rest is for the C phase. This is for C phase. All are identical. Just we need to change the device names. So we have one modulating signal here. So this is A phase modulating signal, and this is B phase modulating signal, which is 120 degrees delayed, and this is further delayed by 120 degrees. That is for C phase. Right. So this is the carrier signal. So each carrier signal, so this FCR is the carrier frequency. So you can see that which is vary from +1 to -1. I think FCR I considered as so carrier frequency I consider as 1000 Hz, 1000 Hz or 1 kilohertz, and the amplitude modulation index MA. So this is 0.95. So MA I have given here. So this is MA. So MA I have given here. This is 0.95. Right. So here each this is one carrier one. So the carrier two should be delayed by 90 degrees, right? The carrier two is delayed by 90 degrees. So this is a transport delay block. So you can hear, right? The transport delay block. So this is corresponding to 90 degrees. So 1 by FCR, so that is corresponding to 360 degrees. So 1 by 4 times FCR, so that is corresponding to 90 degrees. So this is corresponding to 90 degrees. So here, the third carrier is further delayed by 90 degrees. So output of this delayed carrier, so again I delayed by 90 degrees. Right. So again for fourth one, the third carrier is delayed by 90 degrees. So that means you are getting all the four carriers. The first carrier is as it is, second carrier is delayed by 90 degrees, third carrier is obtained by delaying the second carrier by 90 degrees, fourth carrier is obtained by delaying the third carrier by 90 degrees. So if you see this, a common scope here, so which is correct. The first one is the modulating signal. So carrier 1, carrier 2, carrier 3, and carrier 4 in a scope. So here this is the comparison, right? So this first one, these are all carrier and modulating signal comparison. So this one is a modulating signal on the top, and you have the carrier one here. So carrier one I'm comparing here less than or equal to. So this is S11A, right? So this is S11A and S21A. For not get S21A, you can see here. So this is S11A and this is S21A. So here this first bridge S11A and S21A. Similarly, for the second one, so this is S12A, S22A, all are A phase only. So this is S12A, S22A. So that means this is 1, 2, right? And in the bottom side, so this is this device and this device. So now the third carrier is supposed to control this S3A, 2A and S42A. So this is S32A and S42A. You can see here. So this is S32A, S42A. That means as we discussed, it is in U shape, right? So first this device, next this device, third, fourth, fifth, sixth, seventh, eighth, likewise. So last carrier, so which is supposed to control these two devices. So that is S41A and S31A. So this is S31A and S41A. The order is important here, right? So here if you observe that, so this S31A is out here. So this is S31A. It is U-shaped, right? S32A here and S42A, S31A and S41A, right? The same thing is repeated for B phase and C phase as well. The same procedure you need to repeat for B phase and C phase as well. Understood? So now I will run this. So this carrier is same. This carrier is same for all three phases. So only thing is this modulating signal will change. And here, so this you can directly copy. So instead of A, this is B here. So this is B here, and this is C. So here the good thing is that in a larger systems, so we need to properly name the devices like A phase, B phase, C phase, or S1 or S1, S2, S3. You need to properly name it, otherwise it leads to confusion. So here this is the carriers and the modulating signals. See here these modulating signals are properly displayed. This is this you can see this green one, red one, and the blue one, and this purple one. Right. And you have one, I will show you for one modulating cycle. You can see here. If I reduce the carrier, I will reduce the carrier size so that you can clearly see. Just I will make it 500. You can see, right? You can see the carrier arrangement. Right. So now if you see the output voltages, output voltage for this is a line voltage, like A phase, VAB, VBC, and VCA line voltages. Similarly, this is a phase voltage, right? So this one will be the phase voltage, right? And also you can see the harmonic spectrum. For seeing the harmonic spectrum, what we can do is that we need to go this power GUI block. So go to tools and the FFT analysis. So in FFT analysis, okay, so this one is the phase. Yeah, this is line voltage. This is the one. And the start time, so maybe you can change the start time as maybe some point or one cycle or something. And usually for THD, you need to consider somewhere between 3 to 10 cycles. This is the red one, is the highlighted portion. This is the 50 Hz is the frequency you need to consider. Right? So here the maximum frequency selected is just 1000. So we'll slightly make it 10,000 for better visibility of the spectrum. See here, I think this 10,000 is somewhat high. So we'll make it 4,000. See here, right? So if you observe that the THD, so that is around comes around 27.35, right? So 27.35 is the THD, so that is uptime. And also see that these sideband harmonics, so which are centered around this value, is 20. The sideband harmonics are centered around 2000. So this is corresponding to, you know that, right? We kept only 500 Hz carrier frequency, so that means MF is 10, right? So MF is 10, so that means, as we discussed, so it is M minus 1 times MF. M minus 1 is 4 here, so that is 40. So 40 corresponding to the harmonic order, you can change it to harmonic order here. So you can change it to harmonic order. So this is corresponding to 40. Right? So we are producing the sideband harmonics at around 40. Similarly, we have sideband harmonics at around 80 also we can see. If you have change this see here, you can see that, right? At around 80 also you can get the harmonic spectrum. Similarly, 120 you'll get another spectrum. Right? Understood. So this is about the phase shift PWM technique. Similarly, we'll see how it will be there for a level shift PWM techniques. I will just uncomment this one. Right. So this is a level shift PWM technique. Right. So everything is same. So everything is same. So only thing is that so we need to change the carrier orientation. Right. So here the modulating signal is remains same. So here the carriers you can see that, right. This is first carrier which is vary from 1 to zero point 0.5. Second carrier which is vary from zero point 0.5 to 0, and the third carrier which is vary from 0 to minus zero point 0.5, and the fourth carrier which is vary from minus zero point 0.5 to minus 1. Right. So rest of the things are same U shape, everything is same. Only thing is that so we need to change the carriers. Okay. So if you run this one, so you can see here. See here. Okay. You can see here the carrier arrangement, right? This carrier one, two, three, four, right? All are vertically disposed, and you have a common modulating signal as the mod. In the color is the modulating signal, sinusoidal waveform, right? So now we can see the we say output voltages, line voltage and phase voltage. They are something like this line voltage here. Because why we have very one line, sir? Because we selected the carrier frequency very small. So usually 5,500 is very small. So you slightly increase the carrier frequency. We'll make it 2000. See here, right? So this is the output voltage obtained from the level shift PWM technique. You can see here, right? The waveforms are as close as to a sinusoidal waveform. Right? So this is the line voltage, and you can see the phase voltages here. So these are the phase voltages. You can see five levels. This is G1 minus 400, minus 200, 0 level, 200 and 400 level. So we can also see the harmonic spectrum. So go to tools and the FFT analysis. Okay. This is line voltage, and again this is 50 Hz, and we need to leave some initial cycles. And we will consider 3 cycles. Okay. The maximum frequency maybe you can consider 5000. Okay. Harmonic order. Okay. See here. So here we have considered 2000, right? So 2000 H. So 2000 H corresponding to MF is 2000 divided by 50, which is 40. So here, as we discussed, the inverter frequency is MF, right? MF, another inverter frequency, carrier frequency are same. So that's why here the harmonics are appeared at 40. So harmonics are appeared at 40 here. And also we can see that the THD is just 17.29. So earlier we got somewhere around 28, 29%. So now it is only 17.23. So this is how we will simulate the this phase shift PWM and the level shift PWM techniques in MATLAB. Understood. So next we move to the other topic, so that is grid integration. So how we need to integrate this grid to the grid, especially when this two level is involved or when the multi-level inverter is involved. So first I will discuss some of the basics of this grid integration. Right? You might have know that. So just we'll quickly see what are the basics that are there here. So am I audible?
Yes, in audible. Since you're audible.
Yes. I think my screen is visible, right? So now we will discuss some of we quickly discuss the grid integration, so especially the decoupled control of the inverter voltage, inverter currents. So let us consider some inverter here, right? So we need to integrate this inverter to the grid. So we need to integrate this inverter is to grid, and this inverter is connected to some DC source. So this DC source may be a PV source, or it may be some wind energy, or that is obtained from after converter, that is DC wind energy. After that, we normally keep a converter for AC to DC conversion, and that DC converter, or it may be a energy storage system, or it may be a battery, or it may be supercapacitor, or anything, right? So we have some DC source, right? So here, let us assume that we have some PV is installed here, right? And this is producing some current, some power it is injecting. So we need to inject power into the grid, whatever the generated power, so that we need to inject into the grid. Or else let us assume we have energy storage system is there. So in this case, the power is bidirectional, right? So depending on your requirement, so we need to inject power into the grid, or else we need to charge the battery from the grid. Right? So for this, so what you might have studied or might have aware of that controller, right? So which is normally known as the decoupled controller or the controller, right? So for decoupled controller, the basics are you have the utility grid is there. So from that, so we need to convert this into the whatever the grid voltages and the inverter voltages or the currents are same, right? Because the series connection, all currents are same. So these things you need to convert into ABC to DQ reference frame. So from that, we need to implement this DQ current controller. So from that onwards, so you will get the reference inverter voltages in DQ reference frame, and here so we need to convert this back into ABC reference frame, and we need to ultimately implement the PWM technique, right? So here whatever earlier I shown like level shift PWM technique or any PWM technique, right? So that modulating signals we are choosing, right? So whereas here, so we need to obtain the modulating signal from the controller, right? So we need to obtain the modulating signals or from this modulating signals from the controller. So in case of previous whatever I shown so far, so that means you are generating your modulating signal. So whereas here we need to generate the modulating signal also based on your requirement. Okay. So here, depending on the algorithms, many things are possible. Like for example, if you have a DC source is there or some battery are connected, right? So here your objective may be different. So first thing is that your objective may be, for example, you have connected battery here. So battery charging. So when you're charging the battery, you must maintain some voltage across the battery, right? So that means you need to make this DC link voltage. So we need to keep. So that means we need to control or we need to regulate this DC link. So that is our objective. So another objective is that so you need to inject certain amount of active power P, and also you need to inject certain amount of reactive power Q. Sometimes you will make it zero, depends. Sometimes we will inject some reactive power, generally P and Q. So it will be controlled based on the your requirement. So usually we have frequency fluctuations will be there. The frequency active power will be controlled. In case of voltage fluctuations will be there, and that under that case, this reactive power control, this reactive power is controlled. So that means you have three control objectives that are possible. So one is the DC link voltage VDC. So another one is the active power injection and the reactive power. So your three objectives you need to fulfill. Right. So here, so you know that, right? The first thing is that when you have a DQ control theory or the reference frame transformation, so you might have studied that. First thing is that we will transform everything into the synchronous reference frame or the DQ reference frame. So where in DQ reference frame, so you will get these powers, or this we can decouple the active component and the reactive component of current. So meaning is that, so when you decouple the currents here, so whatever the grid side currents or the inverter currents, when these are the currents, so when you decouple or we transform into DQ reference frame, so there is a possibility that, so we can individually control this active and the reactive power. So usually this direct access current will control the active power, and this IQ usually control the reactive power Q. And this VDC regulating the DC link voltage, which is also similar to active power control. So therefore this can be done by controlling the active power command. So meaning is that, so ID can able to control the DC link voltage and as well as the active power. So whereas this IQ whereas this IQ can able to control the reactive power. So what exactly means decoupling? Means individual control of both active and the reactive power. So that means in one case, PV, for example, PV is generated some 10 kilowatt power, right? You want to keep zero reactive power. So P is 10 kilowatt and Q is 0, right? So that means the control is independent. In this is one case. So other case, maybe you have 9 kilowatt power, it is generated, and this is also 0. So that means while you are controlling the active power, the reactive power control should not be disturbed. Similarly, when you are controlling the active power, the reactive power means when you are controlling the reactive power, this active power control should not be disturbed, right? And another thing is that, so when you are maintaining the DC link voltage, so when you are maintaining the DC link voltage, so normally, so we need to control this ID fixed. So we need to control this ID value. Understood? So we'll quickly see so what exactly it is. So this is the decoupled control technique. So these are the utility grid side voltages. So this is VAB is the grid voltages, and VTABC is the inverter side voltages. So VTABC is the inverter side voltages, and this is the current, right? So here this inverters and this grid, so we normally operate in parallel. So that means, so this grid and this inverter, if you observe that, so this is like a this kind of system. So we have one side and receiving end side. This is a transmission line problem. But thing is that this is a sinusoidal waveform. So whereas this one is not exactly sinusoidal waveform. Instead of that, we have some PWM waveform. Right. So here, depending on, for example, if you want a real power exchange from here to here, so you need to maintain some phase shift. You know that, right? So this V1, V2 by X sine delta. This delta is with the phase shift that you are supposed to maintain for a real power transfer. Similarly, this inverter and this grid voltages, so we need to maintain the phase shift. So how much phase shift we need to maintain? So that all depends on how much power you are injecting into the grid or you are dragging from the grid. So that means these two are in parallel, but thing is that the power control can be done by changing the angle difference between the inverter and the grid. Right. The first thing is that, so this is VTABC, IABC and VABC, right? Here we first transform this into ABC to alpha beta reference frame, and again we'll transform back into ABC reference frame. So before that, we need to understand that so the powers in DQ reference frame, for example, if you consider P, so it will be VD into ID plus VQ into IQ. So this is your active power. So in case of reactive power, so it is usually like this VD into IQ plus, minus VQ into ID. So this is your reactive power in case of in DQ reference frame. So if you are, you know that, right? In case of DQ reference frame, it is everything is synchronized. Under this case, so VQ value will be equal to 0. So that means your P is equal to VD into ID and Q is equal to VQ into IQ. Sorry, VD into IQ. Right. So meaning is that if you want to control this P, right, for example, I want to inject some certain amount of 10 kilowatt power or something, right? So MPPT is observed that you can able to inject some 10 kilowatt of power into the grid, right? So that means your P star is equal to, for example, 10 kilowatt, right? So accordingly, you need to calculate the ID star. So this ID star will be equal to, as from this relation, okay, so this ID star equal to this P star divided by this VD. So that gives you the ID current. Similarly, this IQ star, if at all you want to control some reactive power, so this will be Q star divided by VD. Understood. So these are important parameters. So setting up the ID and IQ reference values. ID and IQ reference values. You know that, right? You can sometimes, you know, the transformation sometimes. So this is the magnitude invariant, or there are other alternative equations are there, like it is 3 by 2 times VD into ID plus VQ into IQ. This is for if you are choosing a different transformation coefficient for the DQ transformation, right? So anyway, we're not discussing that to avoid confusion. So let us assume that the transformation is done based on the power invariant expressions. Right. So this will gives you the ID star and IQ star reference values. Right. If you want, you know that, right, PV is able to generate certain amount of power, like 10 kilowatt power, it is able to generate it, and you want to inject that power, and this P star is equal to the 10 kilowatt. So that means accordingly you need to calculate this ID star. Right. So this your ID star will be P star by VD. IQ star will be Q star by VD. Right. Similarly, if you want to control the DC link voltage, right? If you want to control, or if your objective is to control this voltage, so that means in this voltage, again, you need to control the ID value. The first thing is that you need to regulate this voltage at certain value. Right? So this is your VDC reference, and this is your VDC actual, and you have one PI controller here, and this will gives you the ID star plus minus. So this one is known as voltage oriented control, VOC, voltage oriented control. So whereas this one is known as grid active and reactive power control, and also grid power control, GPC or GA RPC, grid active and reactive power control, or like this. Right? So here this objective is to maintain the DC link voltage. Again, if you want at the same time, if you want to control the reactive power, so again this IQ star will be equal to, so this Q star divided by VD. So this will, this first object, these two are different things, right? This one will control the VDC and this will control the reactive power. So this will control the active power and this will control the reactive power. P it will control, Q it will control. So here it will regulate VDC, and whereas this one it will control the reactive power. Okay. So basically there are two control approaches are there. One is the voltage oriented control and the grid active and reactive control. So in case of VOC, so we will control VDC and Q. In case of grid active reactive power control, so we will control P and Q. These two are the different control approaches. Okay. So now based on these equations, the first we'll convert this into ABC reference frame. From this ABC reference frame, we'll convert into the DQ reference frame. So these are the individual equations. So these are the individual equations of this when you are applying KVL for this one. So you will get these individual equations in the DQ reference frame. Right. So next step is that, so as we discussed, these are the two individual equations. So that is obtained from the DQ reference frame. If you see deeply, or if you see this one, right? So this one is the voltage drop in the resistance. So this one is voltage drop in the coupled inductor. So this is the coupling inductor. We're not talking about this. So this one is the coupling inductor. So why this is required means, so this is voltage source. So this is also voltage source. We are trying to connect these two voltage sources in parallel. So therefore, so we must require something to observe the loss component, another voltage drop. So meaning is that, so this voltage and this voltage, they're trying to be equal, right? But it's never be equal. So there will be some voltage drop, right? So that voltage drop is absorbed by this inductor. So the voltage drop is absorbed by the inductor. So that means, in other words, we are controlling this inverter voltage drop. We are controlling this inverter voltage drop, or if you estimate this inductor voltage drop, so we can actually estimate the this inverter voltages. So this is known to you. So this is the one you're trying to find out. So this is the one you're trying to find out, right? So that means if you estimate this voltage drop across this inductor and this resistor combination, so we can able to identify the inverter expected voltages. Inverter expected voltages. So inverter expected voltage means that are equal to the modulating signals. Inductor inverter expected voltages are equal to the modulating signals. So that means this voltages, current, right? But only thing is that, so how much voltage drop across this element, that you don't know. So for that, what we can assume that, so if you read, this is the equations, this is the voltage drop, right? So this is the voltage drop. So we assume that this voltage drop is equal to some UCD. So here also, so this voltage drop is equal to UCD. All right. So rest of the things are same. So you are interested in this VTD. So that is the inverter voltages in DQ frame. So we are interested in these two parameters. All right. So how we are estimating this voltage drops? By using a PI controller. By using a PI controller, so we have estimated this voltage drop. So come to this figure. So you have the reference d-axis current here, right? So how this is obtained? So this reference d-axis current is, as we did it, P star, so which is equal to, this ID star, so which is equal to P star divided by VD, right? So this is the actual inverter current. So we are comparing this one. So this is your error signal. So this error signal you are giving to a PI controller. So this will gives you the voltage drop in the inductor. So this gives you the voltage drop in the inductor, and we are adjusting this drop here, right? So we are adjusting this drop here. This is the modulating signal you require, right? So this gives you the drop, and this is VD. We are adding VD here. So here adding VD here, and this one is the coupled term, right? So this depends on the coupling term. This is minus LT omega ITD. So you can see here, right? So this is ITD. So this ITQ. So from this ITQ minus omega LT. So this is the term we are adding, right? So here why we are adding this term is that, so to decouple the active and reactive terms, right? You know that, right? So because of this current, so this one is the loss, and we are compensating this loss indirectly. Okay. So this is gives you the VTD. Similarly on the other side, so this is your ITQ, and this is your reference ITQ. We are comparing here, and this is the voltage drop in the inductor plus resistance, and this is the VQ we are adding here, and this one is the decoupled component here, right? So this gives you the VTQ and ITQ. So these are the inverter voltages or expected inverter voltages in DQ reference frame. So these are the expected inverter voltages in DQ reference frame, right? And here, so what is next step is that, so we know that, right, this DQ reference frame, these are the inverter expected voltages, means indirectly we obtain the modulating signals. We obtain the modulating signals, right? So that means these two things. So what we will do is that, so we have this DQ to ABC transformation, so that gives you the modulating signal for the inductor or inverter. Right? Understood? So what we are doing is that, so we are measuring the grid voltages in ABC reference frame. We'll transferring into DQ reference frame. We'll do all the calculations and we'll obtain the inverter expected voltages. The inverter expected voltages again in DQ reference frame. We'll transfer into ABC reference frame. From ABC reference frame, so these are the modulating signals we obtained. So from this we can implement the PWM method. So from this, so we can actually implement a PW technique. Alright. So there is some small thing is there, right? So one thing is that normally modulating signals usually vary from +1 to -1, right? Modulating signals usually vary from +1 to -1. But whereas these signals are full voltages, these are not normalized or these are not in per unit. So what we can do is that we need to normalize this one. So before giving it to the modulating signals, because modulating signals are ranging from 400 to whatever the DC link volt is, 400 or 700 to -700 volts. But your carrier signals which are vary from +1 to -1, right? So therefore it is not fair, right? So therefore what we can do is that, so we will normalize this one. After that, so we will normalize this one. So for that, whatever we are obtained, right? So we need to divide with VDC. We need to divide this with VDC or VDC by 2. So that means indirectly we are converting into per unit form. Right? So usually we divide with VDC or VDC by 2. So that gives you the normalized modulating signals, so which is usually vary from +1 to -1. Your carriers also vary from +1 to -1. So therefore, you can easily control the inverter. Right. So this is overall control what we discussed. Right. As we discussed, if you are VOC voltage oriented control, so it is PI, P into I. So just forget about this one. It is 1 by VSD. Okay. So here also, this is I consider for the different transmission or transformation coefficient. Right? So first step is that, so grid voltages will convert into ABC to a DQ frame. So this is ABC to DQ frame. So we'll do all these things. So how this ID star is obtained? From this, either this one or this one, only one. Right? So Q star, it is usually 0, right? So this is obtained from this. So this gives you the IQ star here. So this is IQ star and this is ID star. Okay. So we have PI controller. After PI controller, this gives you the drop component in the inductor. So this also gives you the drop component inside the inductor. So we obtain this VD star and VQ star. So this is VD star and VQ star. So what we will do is that we will normalize this one. That means we will divide by 2 VDC or 1 by VDC. It's normalization. And after that, so we'll convert this into DQ to ABC frame. So you'll get the three modulating signals. Three modulating signals. So from these three modulating signals, so we'll implement some PW method. So from PW method, it will give the firing signals for the switches. Clear? So now the thing is that, so where exactly this multi-level inverters or these inverters will use? Like what extra things we need to consider when you're using the multi-level inverters or something. Like the first thing is that, so when you are using a two-level inverter or multi-level inverter, So up to this procedure, it is same. Up to this procedure is same. This entire procedure is same, right? So this procedure, like all these things, is same. So no need to change this one. So this entire procedure is same, whether it's a two-level inverter or the multi-level inverter. Even this is also same. So this procedure is also same. Only thing that changes is this PWM. Only thing that changes is the PWM. So rest of the things all are same. Only thing, so when you have a multi-level inverter, that changes the PWM block. So that is changes the PWM block. Rest of the things are same. No need to change anything. Right. So depending on what kind of inverter you are using, like if it is a diode clamp inverter or the cascade edge bridge inverter or T-type inverter, your PWM technique will change. Your PWM technique will change. And another important thing is that, so you have only one DC source here. So you have only one DC source. So let us assume it is a three-level inverter, right? So let us assume this is a three-level inverter like this. So now you have two DC sources are there. If it is three-level inverter, in two DC sources are there. If at all you want to control this DC link voltage, you need to control these two capacitor voltages. Right? You need to control these two capacitor voltages. Earlier you have only one capacitor voltage, so that what you did is that, so here, so VDC you have only one capacitor, so this compared with the VDC reference, right? And you have one PI controller, so that gives you the ID star, right? But now you have two capacitors, right? And thing is that, so you need to balance these two capacitors. There are several methods are there. One is the connecting some extra circuits here, some auxiliary circuits like this to balance the capacitor voltages. That is one method. So another method is that using some techniques like the uh, this is using some techniques like the model predictive control or something. So that is another method, right? Or else using some space vector modulation techniques such that we can balance these two capacitors. A lot of methods are there. Or another simplest method is that in case of simplest method is that this is sum is there, right? Another simplest method is that just by using some PI controllers only. So let us assume this is 350 volts and this is also 350 volts, and the total is supposed to maintain 700 volts. Right? So here two PI controllers or we need to use. So this is sum of two DC link capacitor VDC1 plus VDC2. The sum is compared with the 700 volts here. All right. Let us assume you will get one ID star here, some small value, and we have some minor loop here. So this is another loop. So where we do is that, so the difference between these two, so that is VDC1 minus VDC2. Under steady state case, it's supposed to be 0, right? So this is compared in another PI controller. So it is also generate some ID star. So these two IDs, so we will add. So we will add. So that maybe gives you the ID star. Alright, like this. Right. So you can use some auxiliary circuits or you can use some advanced controls like model predictive control or the space vector modulation technique with some small improvements, or else we can use this multiple PA controllers to increase or to effectively balance the capacitor voltages. So rest of the things are same. All this decoupled control or everything is remain same only. Right. So now we will see in the simulation. Am I audible?
Yes, sir.
Yes, sir, let me share my screen.
You are audible, sir.
Yes, sir, let me share my screen. Yeah. I think my screen is visible, right?
Yes,
It's
yes, sir.
visible, sir.
Yeah. So one side, if you see that, right, this is how we will integrate to the grid. So one side on this right hand, on the left hand side, you can see that, right? So we have one grid. is there, some AC source is there. I consider some 415 volts grid, right? 415 volts. These are the three voltages. This three phase 415 volts, and here I'm measuring the current. So here one important thing in the grid integration is the current directions. Right? The current directions are important. So that means what way you're controlling, whether you're injecting to the grid or we are currently are now the current is this. This one is what the current I'm drawing, current I'm measuring toward means away from the grid, right? That means in this direction from the grid to the load direction I'm measuring. I connected some coupling inductor here. Resistance we can neglect. So one coupling inductor I connected here. So now I connected one inverter. So this is the two-level inverter I connected here, and I connected one capacitor. And this one I modeled this. Let us assume this one is a battery. Model this battery as a current source, a controlled current source. I assume that the battery plus 20 means it is indicating in this direction. That means 20
இன்னைக்கு சீரியஸ் ஆகுது
uh, plus 20 meaning is that from the battery the current is away from the battery. That means the current is flowing from the battery, that is 20 amperes. So that means if you measure the current in this highlighted one, so you will get 20 amperes of current. If it is minus 20, for example, if you made it minus 20, so that means the battery is charging, right? So in this case, it is battery is discharging. If it is make minus 20, so the battery will be charging, right? This 20 means the power flow is supposed to be from this battery to the grid, right? That means the battery is discharging, right? So that means the power flow is from the battery to the grid. If I make minus 20, the power flow is from the grid to the battery. Understood, right? I just model. You can also model same way. You can also model the PV. Normally, PVs and batteries, it is in a bigger system. They usually model as a controlled current source, and we will give you the. So how much power we are injecting? So that depends on the, for example, this 20 amperes current, right? Let us assume that I am maintaining 700 volts here. So that means the power that drawn from the this entire thing is that 700 into 20. So that means it is 14,000. That is 14 kilowatt power, right? So this voltage, if I maintain 700 volts here from the controller, and the current it is injecting 20 amperes, so that means so 700 into 20, so that means around 1400 watt power. So that is injecting. Understood, right? So now we come to the decoupled controller part, as we discussed. The first thing is that we need to measure the grid voltages, and we need to convert this into DQ frame. So I sensed the grid side voltages here, VABC and IABC are the grid voltages here. I transform this into ABC reference frame. So for transformation into ABC reference frame, you need to know the phase angle or this angular information. So for that you need a PLL. So this is a three-phase PLL. So from that you obtain this omega t, that is synchronization signal. So from the synchronization signal we can obtain the DQ0. So we got the VSD, VSQ. So this V0 is equal to 0 under the balanced case. So this I0 also 0. And these two are the grid side voltages in the DQ reference frame, and these two are the grid side currents in the DQ reference frame. Understood? So next thing is that setting up the things like so I want to now I want to maintain the DC link voltage here. So what we can do is that I sensed the DC link voltage here. So this is the DC link voltage. I sensed this DC link voltage here, right, by using this. So this is the VDC sensed one. I want to maintain this DC link voltage at 700 volts. So we can maintain this 700 volts here. So this is you're comparing with 700 volts, so plus minus, and you have PI controller. So this gives you the ID star. Right? As we discussed, this gives you the ID star. So next thing you done is that so you need to control, also need to control the reactive power. I want to make the reactive power 0. So that means both currents and grid side voltages. So both are in phase. Right. So this is reactive power. So I made it 0. Right. So as we discussed, P equal to or Q equal to VSD into IQ. So this gives you the, that means this gives you the IQ star. This gives you the ID star and this gives you the IQ star. So rest of the things are same. So what we done is that implementing the this one, implementing the right. So implementation of this one, you got this ID star, ID reference, you got ID reference, and rest of this implementing this controller. Right. You can see here. So here VST is there. So this is omega L. So omega is 2 pi F into LAC inductor value. So plus or minus plus PD minus PD likewise. So we added all this. We also added this VST component. Right. So here we got these two. We got the inverter expected voltages in the DQ reference frame. So along with this V0, and this is the normalization thing. So I divide this one, VDs are divided modulating signals by VDC by 2, right? So VDC by 2. So now these are in per unit. Normally we can connect, these are DC values, right? DQ frame values or DC values. Sometimes some noise will be there or something will be there. So usually you can connect some small low pass filter. You can connect some small low pass filter here, right? So just to reduce the noise, this is optional, right? So you can connect some small low pass filter here. So this is dq0 omega t, and we have abc reference frame here, right? So from dq0 to abc reference frame, so now we obtain the modulating signals, and these modulating signals are compared with the triangle carriers here. So from this triangle carriers comparison, so we can generate the switches for the individual phases. This is S1, S4 for A phase, S3, S6 for B phase, and S5, S2 for the C phase. Right, understood. So this one is the power measurement block. So just I want to see whether the powers are properly measured or not. So this is a power measurement block in the ABC reference frame, and this is in PDQ reference frame. This 2 by 3 is additionally connected to the, just whether to check all the powers. This is for coefficient things. Right? So I will run this simulation. I will run this one. So as we discussed, the first thing is that, so we need to check whether the DC voltage is maintained 700 volts or not. This one is working or not. So that is, you can check here. See here, the DC voltage is 700. Right? So it is maintained 700 volts here. Right? So we fulfilled the first objective. So we are maintaining the DC voltage 700. You can see here, this is exactly 700. This is 700 0.2, and this is almost perfectly 700 volts we maintain without any deviation. Right? So next thing is that we need to check whether the source currents are sinusoidal or not. Right? So source currents, you can see here, this is the source currents or the grid side currents. You can see the grid side currents are sinusoidal. You can see here, right? The grid side currents are sinusoidal. Okay. The grid side currents are sinusoidal. Some small switching is there, so we can slightly increase the inductor size, or else we can slightly increase the PWM frequency, so that will suppress these ripples. Right? You can see some small switching is there, right? So you can easily suppress this one by slightly increasing the inductor size, or else we slightly increasing the PWM frequency or carrier frequency, so that will suppress this. Right? So next thing is that, so we kept the reactive power 0, right? So we kept the reactive power 0. So that means the grid is not drawing any reactive power. So that means both current and voltage supposed to be in phase. So now I'm extracting the A phase voltage and A phase current in one scope. So you can see here. So both are in phase, right? Both are in, not exactly in phase, 180 degrees out of phase, right? So why it is 180 degrees out of phase means Now what happens is that the battery, right? So this battery injecting power into the grid, right? So I kept plus 20, right? So the battery is injecting power into the grid, right? So that's why you got a negative power. So grid power negative means the power flow is from the battery to the grid, right? So you can see here that negative power flow. So both voltage and the currents are out of phase. You can see that. So both are in out of phase. So this is both are in out of phase, right? So that indicates that the power flow is negative. Right? Understood. So another thing is that both currents are sinusoidal. It is in phase, but out of phase. Right. Clear? So next thing is that so whether you are injecting the required amount of power or not. So as we discussed, so this is it is maintaining 700 volts, right? And this current is 20. So it's roughly 14,000 kilowatt of power we need to inject, right? If you see, calculate the active power. So this value is roughly equal to the 14,000 watts, right? So reactive power is supposed to be zero. Some small value will be present, so that is negligible, right? So this kind of values are we can negligible because of switching losses or some control interactions or something, or the currents are not perfectly sinusoidal, right? So we'll still get some small deviation in the voltages. Right? So I will increase this to 30. Now I will assume that the battery is drawing more power, or else I will make it 30 here. Let's assume I made 30. So now it is 30 into 700, right? It's supposed to inject 21,000 watt power into the grid, right? So now we can see here, right? So it is roughly injecting 21,000 here. So reactive power is almost zero, right? So understood, right? So now I will also inject some reactive power, or else I will draw some reactive power from the grid. So I will make the reactive power also. Now I made the reactive power to 10,000. You can see whether it is achieved near 10,000 or not. See here. So active power is remains same 21,000. So reactive power is just 10,000, around 10,000. It is maintaining. Right. So you can also see the voltage here. Right. So you can see here that no longer now they are no longer in phase. You can see some small gap is there. Right. You can see this box. So it is phase difference is there because of the reactive power. Right. You can see they are not in phase. They're not in phase. Right. Understood. Okay. Still, even though in this case also, so we are maintaining the DC link voltage. So now we'll make the reactive power zero, and I will see from the other side of operations. Now we assume that the battery is charging. So I will make this current minus 20. Right? I will make this current minus 20, and we will see. So I'm not done any change here. So every change is just automatic. So you can see here now the current, the power is become 14,000 near, right, positive sign. Right, 14,000 near positive sign. Still the voltage is maintained same. Voltage is maintained at 700 reference value. Slightly the dynamics will change. 700 volts here, maintain 700 volts, right? And the reactor power is almost zero, 510 watts, but we assume that is zero. And this is 14,000 we're supposed to get. So minus 20 into 700, that is around 14,000. And also we can see that the currents are sinusoidal or not. See here, the currents are sinusoidal. If you see that the currents are in phase, so both are in phase. Earlier, it is out of phase or it is 180 degree shifted, 180 degrees shifted. Now it is in phase. Understood? Okay. This is how we will model or we are injecting power or we are drawing power from the source and all. So we can also see the modulating signals here, so which will be vary from the plus 1 to minus 1. Okay, these are small modulating signals. See, that's why you can see some small ripple will be there, right? If you connect some proper value or proper design of this low pass filter, so we can able to make this sinusoidal as possible. So I hope you understand this one. So how we will control the grid side. As we discussed, so this control is remain same. So when this inverter change, let us assume this inverter change to other two level inverter or something, right? So this thing will remain same. Only thing, so this will vary. So this thing will change and this DC link voltage will change. These two will change. So rest of the things will remain same. The rest of the things will remain same. Alright. So let us consider a three-level case. So this is a three-level T-type inverter. The same circuit, instead of two-level inverter, I just used a three-level inverter. So I just connected a load here. Instead of load, I just connected some resistance here. Right. So which is AC to DC applications. We have AC to DC application here. I just connected resistance, and here two capacitors are there, right? So one capacitor voltage is VDC1 and other capacitor voltage is VDC2. This is a T-type inverter. Right? So this one is a T-type inverter. You can, as we discussed, you can see, right? One, the sum of the capacitor voltages. Right, this is the sum of the two capacitor voltages. We compared with 500. Here, the reference is 500. So the difference we are comparing with zero. Right. So the difference we are comparing with zero. So we generated some error signal with the difference. So that error signal is added here. So that error signal is compensated here, and we will run this one. And we will check so whether we achieved our task or not. See here, the first thing is that so capacitor is supposed to maintain 500 volts for this case, and I think we have capacitor. One second. So both voltages and currents you can see, so both are in phase, right? So both voltage and currents are in phase, right? In all phases. This is B phase, and this is C phase. Right? So you can see these two capacitor voltages. You can see here this capacitor voltages. The sum supposed to be 500 and the difference is supposed to be 250, right? You can see here. These capacitors form like a chain-like structure. You can see here one capacitor is charging and the other capacitor is discharging. So this is 250 volts and it is vary somewhere between 245 to 255, right? See here, this is how these two capacitors, one is charging and another capacitor is discharging, so that the balance among the capacitors is maintained here, right? So if you have multiple capacitors, it is just maintaining a chain-like structure. So understood, right? So in case of cascade bridge also, so we have some different other methodologies will be there to balance all the capacitor voltages. We'll stop here. I hope you will understand. If you have any questions, please let me know.
If you have any questions, you can ask now.
Any questions? Then unmute yourself.
Unmute yourself and ask questions. See, there is one
There is a
question.
question. So can you suggest the reference price given the for the balance of the capacitor? So there are some papers are there. I will provide these things. I will provide these things. Do you have any more questions?
Actually, can you highlight why there is a capacitor voltage unbalance when gamma rises? Yes, sir.
Yes. So one of the main reason for the capacitor voltage unbalance is the charge and discharge of the capacitors. For example, if we consider here, right? So
Yes.
sometimes the current will flow this direction, or sometimes the current will flow other directions. Right?
Just a
So if
minute, sir.
there,
Yes, can you share the screen?
it's not sure. Unbalance usually occur due to the deviations in the capacitor voltages. So we expect that, for example, the top capacitor and bottom capacitors, we expect that they will charge uniformly. Small deviations like the even some manufacturer tolerances will be there, or some uh, currents injected into one capacitor and the current injected in the other capacitor. The small deviations are there, and the turn on and turn off times are different. So that will produce the deviation in the capacitor charge and discharge cycles, right? So if the deviation is large, in that case, one capacitor will be excess charged and the other capacitor will be undercharged. So this will continuously happen. So at some point of time, what happens is that the one capacitor is fully charged to the DC voltage, and the other capacitor will become zero, right? And entire operation will be means stopped, right? So you will not able to control the current, or nothing can be controlled. So therefore, we need to maintain the capacitor voltages. In other words, we need to maintain this neutral point exactly at its value. If small deviations are occur, so that leads to the DC offset, and this effect is cascade. Some deviation in 1 or 2 voltage is there, right? So that capacitor will be further charged, right? One capacitor will be further charged, and other capacitor will be further discharged, and the difference between the capacitor will be further increased. Right? Okay. So
Okay.
there are methods are there like as we discussed. One commonly used method is using some external circuit. External circuit. External circuits or two-quadrant chopper will be used. For using the two-quadrant chopper, the top capacitor excess charge will be transferred to the bottom capacitor, or if the bottom capacitor is excess charge, that is transferred to the top capacitor. That is one method. And another method is using the model predictive control or some space vector modulation technique. So with some additional switching constraints, so we can able to control the this DC link capacitor balance.
Yes, sir, there is a question.
Solver settings. Solver settings. We can use the normally. We can use what we call ODE 23T or this ODE 23T normally used. Solver for power electronic application, right? And how to choose the DC link capacitor for multi-level interface. So this DC link design is one of the complex things. So this DC link is based on the unit capacitance constant (UCC). So how much uh, things you need to control based on that we need to select this DC link capacitors. I think I'll show you. So there are some references are there for this DC link capacitor balance. I will forward it to you. As we discussed, this one is for the selection of DC link voltage. DC link voltage depends on the what kind of converter you're using or how much energy you're storing and all, right? This is some application. So this is the DC link voltage selection for some application. This is the minimum DC link capacitance is 2 NTM times maximum VDC square by km. So this is for one converter. For other converter, the difference with design will be different. Right? So I will forward this paper. Any more questions?
You can stop sharing the screen. I'm sorry. There's a question, I think so.
Excuse me, sir. Hello.
Yes, yes, sir. Please.
Sir, actually, I'm not fully technically know about the that's transformation of the three-phase synchronous rotating reference frame
Yes,
and
sir.
ABC and from that DQ basic thing. If it is possible here, could you please explain about that? What is the technical theory behind the transformation of into DQ axis from ABC? Before that, from VDC to we are transferring into ABC reference frame, rotate synchronous reference frame. From then we are transferring into ID and IQ, VD and VQ.
The objective of this transfer reference frame transformation is to make the things constant. For example, ABC reference frame is constantly varying, right? So if you want to measure the powers or something, right?
Sir, here you are telling that ABC, here you are mentioning that ABC is same as the RYB phase, huh?
Yeah, exactly. ABC is RYB phase, right?
RYB.
That is time
So
varying, right?
the
If you see that the
time varying,
voltages is
yeah.
Vm sine omega t, some angle will be there, right? So that's
Yes,
time
sir.
varying, and
Yeah.
current is also time varying. If you do the power calculations like VA, for example, you're measuring three-phase active power, it is VA IA plus VB IB plus VCIC, right? So that gives
Yes,
you
sir.
the complex. So whereas if you
Complex.
transform this into DQ reference frame, what happens is that in DQ reference frame, the frame is also rotating, right? So it is like
Yes, sir.
two trains. For example, you're traveling in one train and you're standing somewhere and you're observing
Yes,
the
sir.
frame. Like the train is moving, and if you are
Yes,
in a
sir.
DQ reference frame in such a way that your both trains are running parallelly, and you are standing on one train and you are observing the other train. So how you look the train? It's a constant, right?
Yes, sir.
The same thing
Yeah.
here also in this TQ reference frame. So everything, whatever this VD and IQ are, this will be constant. Right. So in this case, the power wheel is simple. It is VD into ID plus VQ into IQ. That is just a constant. All are DC quantities only. Right. So they are not time
Yes.
varying. Okay.
It's
So
not
it will
time
make the
varying. Yes, sir.
simplification simple. DQ transformations, it will make the simple calculation simple. And also another thing is that whatever the coupling there between the, for example, three-phase transmission line. So there is just some mutual inductance between the A phase, B phase, B phase, C phase, or C phase to A phase, right? So if you're doing the
Yes, sir.
transformation, that mutual inductance will also be removed. So that kind of
Okay.
things are there.
So to
This is
achieve
a very
the
basic topic, so you can refer any online materials or any reference papers.
yes, sir. Yes, sir. Yes, sir. As I told, it's very basic, but the understanding of the this transformation is very important
Yeah,
to find out the control signals of IVD, ID, IQ, like that. Is it, sir?
yeah, exactly. Without transformation, we cannot do this grid integration or anything. Even for space vector,
The
what we
controlling,
saw, this is required. ABC to alpha beta transformation is required. Right.
for controlling that inverter
Yeah.
to obtain the rated voltage and maximum power in all the places it's coming to achieve the maximum power transformation also for
But
achieving for arriving that reference values we are using that transformation. Is it correct, sir?
usually for MPPT technique, this transformation is not very much required because all are in DC only. For grid integration, AC side control,
Grid.
we use this thing.
Oh, yes, sir.
AC
Correct,
side
correct. For integration,
grid integration control, motor side
that
control.
is from the DC source, we need to transfer inverting into AC. For that inverting AC, we need this transformation.
Just we are using this. First, we will do everything into DQ reference frame. We will do our task, right? And after that, we will convert peak to ABC reference frame. This is same thing
Then
we also
again,
use for motor, yeah, motor drives also. For example, you are
yes,
using
sir.
the motor drive. We can independently control the torque and the speed. Right, one
Yes,
ID
sir.
component maybe control the torque and IQ component maybe control the speed like this.
V by F
VPF
controllers.
at the same time
Uh,
maintaining VPF.
yes, sir. Yes, sir. Thank you, sir. Thank you, sir.
Someone has questions, Babu.
Yes, sir. Myself, I asked that
Okay,
question
yours.
about the.
Okay,
But yeah, yeah. Thank you, sir.
okay, thank you.
Yeah, thank you and all. We are closing the session, and tomorrow we'll meet again at in the morning around 8:30. Okay.
So thank you everyone. So thank you for giving this opportunity.
Thank you, DSS.
Thank you, sir.